So all of these are related rates. So we always have to talk about d something dt in those because all of them are referring to how things happen over time. So in number 3, we're talking about a rectangle. Okay, it tells us that the width is half the length. Okay, at what rate is the area increasing? So I'm trying to find how the area is changing. So that's my dA dt, how the area changes over time. When the width is 10, and it's increasing at 0.5 centimeters per second. Since centimeters per second, that's a rate. So it's talking about how the width is changing, so that's my dw dt. It's increasing, so it's a positive 0.5. Remember, you could have decreasing, in which case it would be a negative. So all of these rates, any variable that's changing over time is d something dt. Now, when I'm talking about area, we know area is length times width. No, don't write this down quite yet. If I did the derivative right here, derivative of a becomes dA dt. But length and width are both variables. And if I do their derivatives, what would happen? We'd have to do the product rule with it, right? Derivative of the first, so derivative of L would be dL dt, times the second, plus the first times the derivative of the second. The issue with this is, I could figure out my length, but do I have dL dt? No. So if I don't have any information about how it's changing, I would rather get rid of it before I do my derivative. And that's where this other piece of information comes in. I already told you that the width is half the length. So what that means is if I don't want my length would be 2 times the width. You agree with that if I just multiply my 2 on each side? So now my area becomes 2w times w, or 2w squared. Now we can do our derivative. Derivative of a is dA dt. Derivative of 2w squared becomes 4w, but every time I do the derivative of a variable, what do I put with it? d something dt. Derivative of w would be dw dt. So then we plug in our stuff. So w is 10, dw dt is 0.5. So 40 times 0.5 would be 20. Units, area is always squared, so we are in centimeters, so square centimeters. T time was in seconds. So it tells me at that instant, the area is increasing 20 centimeters per second. 20 square centimeters per second. Do you guys want to do another one of those rates together? Or do you want to try them on your own? Okay. So a plane is flying horizontally, so straight across, and I am quite the artist, so I've got my little plane here. Okay. At an altitude of 1 mile. If you're just flying horizontally, is your altitude changing? No. The only things that we can label with numbers in the beginning are the constants, the things that aren't changing. My altitude isn't changing here, so I can go ahead and say that's just 1. At a speed of 500 miles per hour. Miles per hour, that's a rate, so I need a variable for this. So then my rate, how dx dt, is 500. And passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing. So we had our radar station down here. The distance between them would be that diagonal. So if I want to call that y. I want the rate that's changing, so I'm looking for dy dt. when it is 2 miles from the station. So which variable is 2? The y. Is y always 2? No. So I can't plug it in yet, not until after I do my derivative. If we have a right triangle, what formula might we use with that? I can use my 1 because it doesn't change, but the others are changing, so those are going to be variables. Then to get my rates of change, we do the derivative. Derivative of 1 is 0, so that would go away. Derivative of x squared would be 2x. What does it have to have with it? The x dt, because I'm doing my derivative in terms of time. Equals y squared, that's 2y dy dt. Okay. I don't know my x. Dx dt is 500. Y is 2, and I'm looking for dy dt. So I have to find something to plug in for this x in order to find it. How could I do that? We already know at this particular instant in time, what's our y value? 2. So if at this point in the time y is 2, can you find x at the same time? We know 1 squared plus x squared would have to equal 2 squared at this point. So x squared is 3. So at the instant we're looking at, the x is the square root of 3. So if we divide over, dy dt is 250 radical 3. Units, y was measured in miles, and t was measured in hours. So at that point in time, the distance between the plane and the radar station was increasing because it's a positive 250 radical 3 miles per hour. Are they coming back? So problem number 2 tells us our cost. And just FYI, study guide, it's too much effort. I did not make all of your numbers nice and pretty, but the final, I will. So you might need a calculator for some of the numbers here. Final numbers would be nicer. So part A wants the marginal cost. How is marginal cost related to cost? Just the derivative. So 12 minus 0.2x. Part B, find C prime of 200, which just says you plug 200 in for your x's. If I were going to put this on your test, it would probably be a pretty nice number, like 10 or 100, something you could easily calculate. 200 you could work out, but I would be okay, study guide especially, if you plug that in, you get 32. So then it says, what does it predict? Remember, a derivative is a rate of change. So it tells us the cost is changing. Since it's a positive, that means it's increasing. $32 per yard when, the moment when x is 200, so when 200 yards are produced. Okay, so it doesn't tell me what the cost is. It's just telling me if I'm making 200 yards and I decide to make one more yard, I would expect to pay an additional $32 to get that final yard. So it tells us how the cost is changing at that point. Then I asked you to compare that with the actual cost of manufacturing 201 yards of fabric. So to get your actual, this tells me the increase. So you're going to have to find the cost of 201 yards and the cost of 200 yards. And then we're going to look at the difference between those. So I am plugging those numbers into my original. I had a typo in that. This number's wrong. Nope, that one's not right either. My goodness. I dropped a 0 and then I tried to bring back up something in my calculator and I had something else entered in already. Hold on. Let's see. This is why we don't use calculators on the final, right? Too easy to type something in. Oh, here we go. So for 201 yards, the actual cost is $3,632.2005. For 200, it's $3,600. So if you actually subtract those, the actual cost difference is $32.20. Our prediction was $32. We can see we were off by 20 cents. Okay, so it asked for the actual cost difference and compare it, just 20 cents higher than our prediction.